4-bar linkage is one of the most basic yet useful mechanisms in engineering. It is configured so as to have 1 degree of freedom and so can be controlled with only a single input. The benefit of this is that even quite complex movements can be produced with very little complexity of the input. In the case of the project at hand, a level luffing crane, the output must be along a horizontal line. As can be seen in the image to the left, the cranes are used in harbours and docks in order to move large loads from one area to another. In order to produce a 4-bar linkage that replicates the movement of a level luffing crane, a rough idea of how the crane works is needed. The ground, link 4, is seen to attach to links 1 and 3 with pin joints of 1 degree of freedom. Links 1, 2 and 3 are all attached with pin joints. The input link is link 1. The joint between links 1 and 2 is at the end of 1 and 2/3 from the end of link 2. This allows for a greater range of motion of the crane. In order to find a 4-bar linkage producing a coupler curve with a substantial horizontal line, some time was spent on a 4-bar linkage simulator with the following results. The first part was manipulating the length and position of each of the links with respect to one another. The next part is assessing whether the coupler curve produced meets the requirements. In the case of this mechanism shown, the requirement of a substantial horizontal line is met, and so the measurements of the links can be taken and adjusted accordingly to maximise the horizontal straight line on the coupler curve in the MATLAB code. Before we commenced the coding process, we first identified the variables the code would need and the results that the code would need to produce. We felt that this was the best way to go about it, as it would allow us to design the code around the inputs given and the outputs that were required. The purpose of the code was to find the limits of motion and draw the coupler curve for a 4-bar mechanism. The inputs that were to be used were the lengths of the members and the position of the coupler point. Next in the process of designing was deriving the equations that were going to be used to do the calculations. This was all done using the theory that we have learnt in class and some trigonometry. These equations formed the basis of the calculation part of the code. There were plenty of tweaks that were done to the equations when it came to the testing part of the assignment, and therefore the final equations used were slightly different to these. We went about testing in a slightly different way to most. The testing was done as new parts of the code were developed, so as we coded through the different sections in our flowchart, we tested each section. The whole coding process is described in the report. The last bit of testing done on the whole program was different member lengths being input to clarify that the code was working as it should. Though the code was working as it should, we realised the speed of the simulation would change based on the user's input for resolution for the graph, as it would change the increment steps. So through a few more tests, we worked out an optimal speed and resolution for the increments and simply hard-coded this in, instead of allowing the user to choose these values like previous versions of the code, making it easier to use. After these tests, we confirmed that the code was working exactly how we would like it to, and we concluded work on the coding section. In conclusion, this has been a good exercise in analytical methods of kinematic analysis of mechanisms, with a specific focus on a simple 4-bar linkage. The problem also required significant use of programming software, in this case MATLAB, in order to analyse and test different potential configurations of the 4-bar linkage.